Good morning. So we are starting lecture 45. This is an introduction to some advanced, very advanced devices beyond the normal devices like bipolar transistors and MOSFETs. What are the other high-tech devices which are used in electronics? I will not discuss much about photonics here. So optoelectronic devices will not be discussed. However, electronic devices, microelectronic devices, nanoelectronic devices, a certain introduction will be given. Before we go to that, let me show you the diagram of propagation delay, which is a very popular plot. Propagation delay against power dissipation. In different, tau p is the propagation delay. Tau p is propagation delay. And there is a power dissipation, and different advanced devices and circuits. The scale is like this. So this is called the power delay curve or power delay plane. The y-axis is propagation delay, and this is the power of very advanced kind of devices beyond the normal MOSFETs and bipolars. I'll still show the conventional devices, how they are positioned here. For example, to start with bipolar, you know that ECL is the fastest. The location here is something like this. This is the so-called ECL bipolar. You see that it is characterized by a very low propagation delay, which is going down towards fractional. This is 1 nanosecond, and this is 0.1 nanosecond or 100 picosecond. This is in that range, typically a few nanoseconds to sub-nanosecond, okay? And power dissipation is quite on the higher side. It is in the range of, in fact, I should have, this is for very advanced kind of ECL. Otherwise, ECL power dissipation lies over this region. In the milliwatts, 1000 microwatt means milliwatt. In the milliwatts, in several tens of milliwatt range to 1 milliwatt. This is the very latest ECL technology. Whereas for the NMOS, which was the competitor to the bipolar in the beginning, and so far as VLSI was concerned, it won the game. But so far as power dissipation and speed is concerned, there are some plus and minus features. Let us see the NMOS curve, which looks, it is not exactly in the scale, but try something I'm trying to show you here. Say for example, in this particular case, it is, this is 10 nanosecond, this is 1 nanosecond. So it is over this range. This is the so-called NMOS. You see that in this case, the power dissipation was appreciably reduced, but anyway, it was 10 times less or 100 times less than that of the best ECL, whereas speed point of view, it was inferior in general as compared to ECL. That is reflected in the NMOS. And CMOS, of course, gradually with the scaling, NMOS technology did not advance much. It advanced to a great extent, but only NMOS technology, because NMOS and PMOS combined together and became CMOS, and the technology developed fast. And this CMOS technology with scaling, there is a lot of change. And as you see that it came down to the range of around, say like this here, to even less than this. This is somewhere. Of course, I am showing you the very latest CMOS technology. Otherwise, NMOS, CMOS overlapped. Resonance intrinsically, please remember that for the same feature size, CMOS is inferior to NMOS, so far as the speed is concerned. However, power dissipation in CMOS is always less. Thus, power delay product in CMOS is very small. That is a positive point for CMOS from the very beginning of the technology. But so far as power dissipation is concerned, CMOS was far better than NMOS, on in fact any other logic family. But so far as speed is concerned, it was inferior to NMOS, to ECL, and all mostly the for so-called MOS. But then with scaling, the CMOS technology got developed very quickly with scaling, and ultimately CMOS has taken a very good, position in the power delay plane. I have shown that this is a practical CMOS, but anyway, CMOS intrinsic delay can go down. Even the curve, let me tell you, the curve has come down to a level like this. The latest CMOS thing. So there has been a shift from the so-called old, little bit old curve to the new CMOS technology, because the power dissipation, the propagation delay, intrinsic propagation delay, could go down even below 100 picoseconds in the fastest CMOS with tremendous scaling, 0.1 micron, 0.15 micron CMOS technology. Then come to the HBT, the heterojunction bipolar transistors, which was a superior technology as compared to the conventional ECL. The use of HBTs in ECL further reduced the power dissipation and also reduced the propagation delay, and the curve was somewhere here. This curve is for HBT. This is the curve for HBT. Typically in this domain, you see that the power dissipation has been reduced and speed is further improved. The whole thing is brought down in the scale in the y-axis towards the origin of the y-axis. Then came the gallium arsenide technology. Gallium arsenide, particularly the Mesfet and GFET technology. In the initial days when CMOS technology did not come to this kind of stage as indicated earlier, where the power dissipation can, in fact, it has been, I'm sorry, the CMOS curve has shifted like this. CMOS is occupying a very good place now. This is the CMOS curve, not even this one. It has been broadened and occupying a big area in the power delay plane. This is a very advanced CMOS. Very advanced CMOS. Please see that this CMOS is not to be seen as a discrete device, but as an intrinsic, as an internal device in the overall VLSI. So far as buffer circuits are concerned, CMOS is inferior still today. For gallium arsenide MESFET technology, the curve is something intermediate, somewhere here. This is gallium arsenide, MESFET and JFET together. You see that here the superiority is if the CMOS technology had not scaled down to ultra small sizes, then gallium arsenide with even 1 micron technology could achieve quite a high speed, very high speed. At the same time, with proper design, it could have very low power dissipation. However, CMOS got the help of miniaturization because the technology is very superior technology. Silicon technology is far superior to silicon technology. As a result, CMOS has gained a lot. So as an internal, as a building block of a VLSI circuit is concerned. Whereas the other device which came simultaneously after the development of MODFET, MESFET, this is called MODFET, and that was somewhere here. This is your MODFET or modulation doped field effect transistor, or sometimes also called HEMT. And so far as very good, you know that in fact the technology is trying to reach the origin of the time and power scale. Ultimately, we need almost zero power consumption and almost zero propagation delay. Therefore, ultimately our aim to reach somewhere here, and frankly speaking, one category of devices has got the ability to go there. That is called Josephson. Junction devices. It's a semiconductor. It's a superconductor tunneling junction called Josephson junction. It has the ability to reach almost zero power, very low power dissipation, and very high switching speed simultaneously. But because again of technology limitations, Josephson junction is a very premature stage. Okay. So Josephson is not a semiconductor junction, semiconductor material. It's not, technology is not semiconductor based. Whereas the rest of the things which I have discussed here, they are semiconductor based. So far as this one are concerned, so-called black solid lines and black dashed lines, this one, excepting this one, they were silicon technology, and they normally do not use any heterostructure. Heterojunctions are not used in NMOS technology or conventional or even the kind of CMOS technology which is being pursued today, excepting for silicon germanium is a very new entrant. Otherwise, CMOS technology, ECL technology, NMOS technology, they were based on single crystalline silicon, a single element semiconductor, but with novelty in design, in novelty in technology, novelty in miniaturization, the speed and power both were brought down, and this is the level of technology which I discussed. But then HBT is a heterostructure devices, and MOSFETs, they are also heterostructure devices. On the other hand, gallium arsenide MESFET is not heterostructure. It is basically on the semi-insulating gallium arsenide, but it is a pure gallium arsenide technology. Single element, single semiconductor gallium arsenide. On the other hand, the HBT heterojunction bipolar transistors and HBT curve, whatever I have shown is a little bit old, but HBT is also coming very close to. In fact, there has been a movement of this curve towards this. HBT is occupying a region like this, doing very well. HBTs are doing very well today, and both HBTs and MOSFETs and HEMS, they are fantastic. And ultimately, if you want to achieve a very low speed, high speed and very low power dissipation, perhaps it is the HBTs and MOSFETs together, they'll have to be used. But there is no substitute of CMOS, frankly speaking, so far as power dissipation is concerned, which you have seen that the curves are going to the left. For these ones, there is a limitation. You cannot have very, very low power dissipation. Josephson devices, they are very small swing, the logic swing is extremely small, and because the resistance is also very small, the power dissipation in these devices are small. At the same time, Josephson tunneling occurs at an extremely high speed. It's not only picosecond, it is far below the femtosecond speed devices, okay. So Josephson has got the ability, but firstly it has to work at a very low temperature. Secondly, with Josephson, mostly the devices are switches, basically passive kind of components. Active components with Josephson, some propositions are there, some work has been done, but its foundation still today it is very much in research stage. But there is a possibility, there is a lot of investment in Josephson research earlier. But in IBM, in fact, it started in IBM vigorously. And that was around the liquid helium temperature, 4 degree Kelvin. Thereafter, people did not like it. As I think you have heard, the materials like high TC superconductors came intermediately, still there. People tried to invent some materials whose transition temperature to superconductivity is not that low. 4 degree Kelvin is too low a temperature. So people thought that if you can make such materials which work at 77 degree Kelvin, which is liquid nitrogen temperature, which is very easily available, then of course Josephson could be a very realistic kind of VLSI circuits. A lot of research, a lot of investments made in successfully it is called high TC superconductors. TC means T suffix C, called superconducting critical temperature for transition to superconductivity. These high TC superconductors, this came during 80s. Let me tell you, this came during 80s and flourished during the beginning of 90s, but then decayed. Frankly speaking, the scenario I do not know much because nobody speaks of this kind of things nowadays. Though there is a lot of tremendous enthusiasm generated with high TC superconductors, and this is going to be used more for the other engineering applications of superconductivity rather than microelectronic and nanoelectronic application. But still there is a great possibility because the physics of Josephson permits to use such devices at a very, very low high speed and almost at very, very low power dissipation. There is tremendous potential, but we are not considering this, but our concern is more towards semiconductors. We have discussed the gallium arsenide Mesfet. Gallium arsenide Mesfet was, I just told in the last lecture that gallium arsenide MOSFET was difficult technologically. So gallium arsenide Mesfet using a Schottky barrier gate instead of a MOS gate was realistic, was developed to a great extent, and I have discussed something about it in the last class. It is possible to realize both depletion mode FETs, gas FETs, as well as enhancement mode gas FETs. And then with miniaturization and use of proper epitaxial techniques, growth of ultra-thin films, this technology has matured to a great extent, and now it is in the market. It is gallium arsenide circuits are available. They are meant for, of course, some specific applications. Where, say for example, gallium arsenide being a wide bandgap semiconductor, it perhaps can be used at a higher temperature. Okay. Gallium arsenide being a wide bandgap semiconductor, it is more resistant to external radiation. So rad-hard, they are called rad-hard circuits. Gallium arsenide basically is a rad-hard circuit. But there are other limitations with gallium arsenide. Technology is still not that matured as silicon technology. Material, material, raw materials point of view, gallium arsenide is not. Therefore, gallium arsenide wafers are still very, 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 very expensive. In fact, 10 to 100 times more expensive than silicon. And thirdly, being a double two-element semiconductor, process temperature cannot be raised too high, to too high a value. For silicon, there is no problem because always there will be arsenic decomposition takes place, and arsenic is highly hazardous. So this is the problem. And finally, of course, gallium arsenide passivation is not an easy task. Just like silicon, which can be very easily oxidized, so passivation is natural. Gallium arsenide cannot be done like that. We have to deposit a film. Although some work has been being done for, that oxidation, nitridation, and etc. of gallium arsenide at high pressure and by different techniques. But till today, let me tell you, gallium arsenide technology, so far as compared with silicon technology, I can say the gallium arsenide is still a child stage. It's a very immature technology. Though it is quite mature in its own scale. If you go back to 20 years ago and today's gallium arsenide technology, there is a tremendous difference. But respect to silicon technology, gallium arsenide technology is not that much, that. But anyway, because gallium arsenide or group 3-5 elements or 5-6 compound semiconductors, there are a lot of advantages. Firstly, we can have materials with different band gaps. We can have materials with different mobilities, carrier mobilities. We can mix them to make engineering it is called alloy semiconductors, whose band gap and mobility and other properties can be tailored, so we can make our own materials rather than depend on only God's gifts. We can mix them with semiconductors to produce newer semiconductor materials with more interesting properties, and those advantages are there in compound semiconductors. Therefore, compound semiconductor researches went on, I think so far as the research is concerned, it went on quite vigorously, and people came forward with newer concepts, newer ideas, which ultimately perhaps will benefit also the silicon technology. So let us discuss some of them. What is a MOSFET? Let us discuss a MOSFET. Called HEMT. It can be gallium arsenide based or indium phosphide substrate based, or like this. Today, gallium nitride is a very interesting material coming up. Silicon carbide is a very interesting material coming up, but traditionally the substrate was gallium arsenide, and there was some interest in indium phosphide in the recent past. Till today, but these are the two important substrate materials. However, there is tremendous potential for gallium nitride particularly. It looks like this. So this is a in simple, schematic cross section of a gallium arsenide based MOSFET called modulation doped FET, or sometimes also called high electron mobility transistor. Modulation doped FET. Or high sometimes also called heterojunction FET. Various names. Here what is done is, you see that this is a semi-insulating gallium arsenide. Okay, this is a substrate. The semi-insulating gallium arsenide has a very high resistivity of the order of 10 to the power 8 ohm centimeter. I told about it earlier. On which we have a very lightly doped N-type gallium arsenide grown by epitaxy called heteroepitaxy. This is of course homoepitaxy. Thereafter, the whole layer is this. This is of course this layer. This is not a separate any layer, but this is electron gas. Let me show it by a dense shade. Then on the top of which, so from here to here, it is a very lightly doped N-type gallium arsenide, very lightly doped. Then we have a N layer of aluminum gallium arsenide, N layer of aluminum gallium arsenide. Okay, and this N layer is also relatively very low doped. Okay, very low doped, practically intrinsic, and this could be totally extended to the top layer. But however, if it is too very low doped for the entire thickness, then the resistance of this from the gate entire resistance will be very high. So what is done normally, that you may have an N aluminum gallium arsenide on the top, not very low doped, but medium doped. Then we have it is called delta doped kind of process. This is not essential, but in this kind of a technology, I have shown a delta doped process where a very thin layer, around 10 angstrom, 20 angstrom thin layer, is doped heavily by a very special technique by an N-type dopant. And of course, these thicknesses are also very small, where this thickness may be around 100 to 200 angstrom. This is about 20 angstrom. The thickness here may be around 500 angstrom. This thickness is again around 300, 400, 200 to 400 angstrom. So I am repeating, thickness of this N-type, N- gallium arsenide, this layer is around 300 angstrom. The thickness of this very low doped aluminum gallium arsenide, this region, is around 100 to 200 angstrom. Thickness of the delta dope region is 20 angstrom typically. Then the thickness of the top layer, which is slightly more doped. It's not, this is N-, but it may be slightly for the control of the, that for various reasons it is not that small doped. Contact resistance, many, and also Schottky barrier adjustment. And then the whole thing looks like this. But it is not never highly doped. Please remember, this is still very, but though I have written this, I could write as N minus minus, and this I write N minus. N minus minus in very low doped, this region, and this is lightly doped. And there is a relatively heavy doping over an extremely small thickness. Now what happens with a bias here, there is the typical energy level diagram from the gate towards the substrate looks like this. And there is a very ultra thin well at the junction of N minus gallium arsenide and N minus aluminum gallium arsenide, okay? Because of the bandage discontinuity, EC discontinuity, conduction bandage discontinuity, and this well is very thin. That is why you have to make this junction almost very abrupt, and it should be a very low temperature process, so that you have a sharply defined quantum well here. So far as electrons are concerned, they are quantum wells, very thin wells. And if you bias it negatively, either gate is biased negatively, then the electron, this layer becomes depleted very easily because the doping over this region is small. Secondly, the vertical thicknesses are also very small. This becomes very easily depleted. And with proper bias, electrons, as in the same process as happens in the case of MOSFET, electrons, there is a point potential well, so electrons either may be sourced from the source, or it may come from the generation recombination process. So what happens as a result? When you bring it down, the electrons from here can go to this, and then it can be turned off. But otherwise, you can have a quantum well, and the electrons, minority carriers here, this is not minority carriers in that sense. This is a very low dope region, please remember. This is otherwise a very low dope region. So in this quantum well, we have called a two-dimensional electron gas. This is a very important thing. Two-dimensional electron gas. 2D electron gas, we call it. Same thing happens in the case of MOSFET. The inversion layer is nothing but a 2D electron gas. The only thing is the electron confinement of that will not be that much small. But here, I am intentionally creating a potential well. In fact, we shall see afterward, these potential wells can be created more successfully by superlattices and other structures, okay? But here, simply the bandage discontinuity we are utilizing, which is otherwise very undesirable. You remember, I have discussed it in connection with HBT. The discontinuity is bad because it creates interface states, and that is bad for the HBT. So what do? We do band grading. I have told you that don't change the composition suddenly, but X is changed slowly over a small thickness of about 200 angstrom in heterojunction bipolar transistor. But here we make intentional use of the bandage discontinuity of the conduction band between L gas, this is L gas, typically 0.3 or sometimes 0.5, 0.5 also, it depends, and this is gallium arsenide. The bandage discontinuity, EC, the conduction band, we are which is due to the nature, and we utilize it for creating the quantum well. And this quantum well, which is flooded with electron gas, a large number of electrons forcefully constrained to remain in two dimension. Their third dimension, that means along Y and Z they are free, along X they are not free. So there is a quantum well, and as a result of this tremendous restriction along the Y direction, what happens along the X direction? So along the X direction there is some kind of quantum which looks like this here, but I can make it, this is along the x direction. Along the x direction, there is a quantum well, which of course actually in our case looks like this. Our case it looks like this, okay? But I could also make some kind of square potential well by other technology. What happens, because there is restriction, you know that in a single quantum well, I do not know whether I've studied in physics, what happens to an electron in a single quantum well, the energy becomes some, you know that there is certain, just like the electron, the energy levels in the hydrogen atom, similarly, an electron in a single quantum well, their energies are discretized, quantized as indicated here. And the difference between them may be quite large depending on how narrow the well is. As a result, an electron, so far as movement is this direction and in this direction is concerned, with a little amount of energy, that means because you have to change energy from here to here to here. There is no intermediate energies available because these are the allowed energy levels in a single quantum well. I'm sure you have studied something about it in your physics course. And same thing happens, similar thing happens here. So far as the movement along the x direction is concerned, there is a confinement, whereas the movement along y and z direction, they are very free. So even at room temperature, it is found that the effective mobility along the channel may be substantially higher than the mobility in normal semiconductor, where x, y, z, all directions the carrier are free to move, okay? Because of the confinement in a two-dimensional plane, the carriers move more freely. And in fact, if you go to a low temperature, 77 degree Kelvin, this mobility may be a very, very high value, which is several hundreds of thousand centimeters, about typically a mobility of mu n of around 100,000 centimeters square per volt second at 77 degree Kelvin is not uncommon. So you can create electrons moving at a fantastically high speed, and therefore what is going to happen? You are going to get a MOSFET with a very high value of transconductance or gain as well as speed, okay? Because the channel conductance is very, very small. And as a result, delta ID versus by delta VG, which is the transconductance, that also becomes quite high. And as a result, such devices can achieve a very high speed if particularly used at a low temperature. This is the beauty of a HEMT or MODFET. Even at room temperature, the electron mobility may be substantially higher than that in a bulk semiconductor or at the surface. Surface, you know, I told you the surface mobility is reduced. But here, because of this 2D electron gas formation in the quantum well, the mobility is very high. And such a device can easily achieve a GM value which is around 100 to about 500 millimole per millimeter. Per millimeter of width, per millimeter of W value. 100 to 500 millisiemens per millimeter of width. This is a basic thing of MOSFET. Okay, the very basic MOSFET structure. The speed can be very, very high. It can easily go down to the range of tens of picosecond, and the gain is also very, very high. As a result, gain bandwidth product of such devices is very large compared to ordinary for the same feature size. That's the advantage. You know, you can have 0.5 micron technology or 1 micron technology, which gives you much better performance as compared to 0.1 micron CMOS technology. So these are some of the advantages here. Smaller are the devices, better may be the performance, but there are many other paraphernalia, many other practical problems. So those people who was working in this particular, in these fields, they are also seeing a bright future for these devices in special applications. Now, in the meantime, there has been a lot of progress in the research on the compound semiconductors, as well as silicon technology, but compounding with germanium, compounding silicon with silicon carbide, germanium, carbon, and all these things are going on. But the main thrust definitely is from the compound semiconductor people, the gallium arsenide people, indium phosphide people, and maybe this cadmium selenide 2,6 compound semiconductor, cadmium telluride people, and people, those kind of people who are working with compound semiconductors. Then gradually, the technology of, there's certain epitaxial techniques developed. For example, one technique is called molecular beam epitaxy, MB, which I have mentioned earlier. Molecular beam epitaxy, where atomic layer, this also sometimes called atomic layer, also called atomic layer epitaxy. Here actually you create a vacuum very high, about 10 minus 11 torr. Such a vacuum normally is called ultra high vacuum. You create a vacuum very low, very good vacuum, 10 minus 11 torr, which is also called ultra high vacuum. Then produce a molecular beam by spatial evaporation technique. People use a kind of evaporator source called Knudsen source. Otherwise, there are various techniques to evaporate the molecules and form a molecular beam. And this molecular beam is allowed to fall on a substrate at a high temperature. So what happens? The molecules roam around the surface, try to find a nucleation site, and that's how epitaxial growth takes place. One can grow atomic layer by layer films, which is epitaxial in nature. That means the crystalline continuity with respect to the substrate is maintained. But then you grow, suppose 2 and 5 atomic layers, or 2 atomic layers, then 10 atomic layers, and you can in situ observe what is happening. There are techniques for in situ characterization in the chamber. This is the picture of MB. Similarly, another thing became popular shortly called metal-organic vapor phase epitaxy. Metal-organic. And similar other techniques came up, very thin doping, transient doping techniques. And as a result, we could add a number of epitaxial films, one after another, producing layers sometimes called superlattice. For example, let me give you an example. We can have things like this. This is, of course, this is maybe this region, sir, aluminum gallium arsenide, and these regions are gallium arsenide. So we can successively deposit films of gallium arsenide and aluminum gallium arsenide, say 20 angstrom, 20 angstrom, 20 angstrom, 20. Like this, you can go on depositing multiple layers, epitaxially. So as a result, what is the wider band gap, so far as the conduction band is concerned or the valence band is concerned, there will be discontinuity. So if I consider electrons, the wells, there will be a quantum, it is called potential wells looking like this. If there is a single potential well made by the epitaxial technique, then as you remember, there will be discretized levels like this. But when you have multiple quantum wells, the energy bands, if I do not consider the effect of the other wells, the energies will be levels, isn't it? But as you remember, when you consider a large number of wells coupled together, the effect of each other, these are called mini bands or subbands. Each things will have a mini bands or subband. So far as so what I can do here, if I just compare with my previous diagram, instead of having a single structure like this, we can have multiple quantum wells staggered over this region. Instead of having here, we can have a number of quantum wells created like this. Okay? And we can make use of these quantum wells for electron confinement in this direction, as well as as a result, we can have a very high GM value and very high speed. This is one application. The other application is the separation between these quantum wells may be so thin, the electrons can easily tunnel from one to next to next. It's called, there can be tunneling of electrons from one quantum well to the next, to the next, to the next, and so on and so forth. Very interesting. Suppose if you have formed a multiple quantum well structure, which is called superlattice. This is called superlattice. If you have formed a multiple quantum well structure like this by one of these techniques, sometimes also done by doping also. By simply doping variations also it is possible to do like this. Because with doping the conduction band comes closer to the Fermi level, higher doping, same technique. But naturally you will not get that much deep wells. But if you want to have deep quantum wells, then the only thing is to use heterostructures, two different semiconductor materials, okay, which matches, there is a very good lattice matching. Otherwise you cannot successfully grow the layers. Now in this case what will happen? Suppose I somehow send an electron here. That electron to go to the other side, what is the necessity? The barrier must be thin, there will be a strong field in between, and secondly this side should be filled up and this side should be empty. So what is going to happen as a result? If I apply a little field, the whole thing will be moving like this, because with the application of a voltage, the actual things will be staircase type with a little slope. And the electrons may find some free space, some unoccupied state on the other side, and this is so thin, there may be a tunneling. If there are two such quantum wells, there may be tunneling back and forth. Tunneling is a process which does not take place only in one direction. There may be, this is called Fabry-Perot interference. That is why it is called resonant tunneling. It's just like a Fabry-Perot interferometer. Photons go on transacting between the two mirrors and go on adding in phase, and that's how we get a very narrow, that's called Fabry-Perot interferometer, basic principle, interferometric principle. Here also, we can have 2 wells or 5 wells or 6 wells. They are so adjusted that electron wave functions. Electrons in this domain, they are represented by wave functions. They can penetrate, travel back and forth, and there can be a resonant tunneling. A tunneling, but with a resonance. As a result, such a character device can give you some kind of characteristic which looks like this. IV characteristics. And you get negative differential resistance regions. we get negative differential resistance regions. These such kind of devices where there are number of quantum wells stacked very close to each other, they are so close that there is a very high tunneling probability.